The next type of spectroscopy we're going to look at is infrared spectroscopy, or rotation, vibration, or Rovibrational spectroscopy. So this occurs in the infrared region of the spectrum, and this is near and dear to my heart. This is what I do downstairs in Hale Lab. And I've got an infrared laser to do this type of spectroscopy. And this is the type of spectroscopy related to our lab that we did on HCl. And so now we're looking at our total energy. Is we have the rotational energy plus we add on a vibrational energy. And then again, this is from the rigid rotor, and the vibrational energy is harmonic oscillator. Okay, so we can take our rotational energy that we used from our previous example of looking at rotational spectroscopy. We'll have our quantum number J. You can add centrifugal distortion. All right, and then the question is, what does the vibrational energy look like? So the vibrational energy is equal to the vibrational constant, either written this way. This is the notation your book uses. So this is nu E tilde, which indicates this is in wave numbers, times V plus 1/2, right? And this is the quantum number V. Or it's, we'll often see it written this way, omega E. This is the exact same constant times V plus 1/2. The omega way of writing is a little bit simpler because then you don't have a nu and a V that look very much like each other. So we know this isn't the whole story, though, because this assumes harmonic oscillator behavior. And as we talked about back when we talked about the harmonic oscillator, real molecules don't follow the harmonic oscillator. So just to recap that real quick, if we have a potential for a diatomic molecule that looks something like this region down near the bottom follows a parabola pretty well, but the whole molecule doesn't. And so we know that the harmonic oscillator is only a model for the actual potential energy. And so we need to add terms that deal with what's called anharmonicity, basically accounting for the fact that this is not actually a harmonic oscillator. And so the way that we do this is similar to what we did for rotation. We do this as a polynomial in the quantum number. So E vibrational will be equal to omega E times V plus 1/2, and then we add the anharmonicity term. So we call this omega E XE. It's another constant. So this is the anharmonicity constant. And this will be multiplied by the square of V plus 1/2. And we can keep going. So there's an omega E YE term times V plus 1/2 cubed, and you can keep going. Right, this is somewhat like the perturbation theory approach where we can have first order, second order, third order. So for our purposes, we'll mostly just limit ourselves to the first order correction, the omega E XE correction. But you can go to higher orders to try and get a better handle on this. And this essentially comes from applying perturbation theory to the harmonic oscillator. So if we only take the first correction terms for the rotations and the vibrations, our total difference in our total energies for our quantum numbers, for our rotations and vibrations, we'll have the vibrational part, omega E times V plus 1/2 minus the anharmonicity, omega E XE times V plus 1/2 squared. And then we add the rotational terms. So our rotational constant times J plus 1 minus our distortion constant times J squared times J plus 1 squared. And of course, both of these terms could have additional terms depending on how accurate we need to be. The selection rules that we have for vibrations are that we can have a change in V of plus or minus 1 and a change in J of plus or minus 1. So for the vibrations, other transitions are possible but weak. So you can have things like delta V equals plus or minus 2. For rotations, they essentially don't happen. Possible but weak. And they're known as overtone spectra. The other thing is to observe a vibrational transition in terms of the molecule absorbing light. For vibrational transition to occur, we have to have a change in the dipole moment as the molecule vibrates. So for vibrational transition, change in the dipole as the molecule vibrates. So if we're looking at something like O2, you still don't see a vibrational spectrum for O2 that you can observe via absorption spectroscopy. Same thing for any homonuclear diatomic, because the dipole moment stays zero even if the molecule stretches and contracts. It is possible for a molecule to not have a dipole moment but to still have a vibrational spectrum if we go to things larger than diatomics. Something like methane, for example, many of the vibrations of methane can be observed via infrared spectroscopy.